All right, so we're back. Everybody here today? I guess I don't. I guess I don't need to record when. Well, no, it's good that you guys have the ability to go back and watch. Right? I was just thinking, I guess I don't need to record when everybody's here. Okay. At least I'll have them for next year in case I need them. All right, so we were on power functions, right? Power functions. Power functions, which include just a number being raised, an x being raised to a number, an x being raised to a positive integer, a fraction, and a negative, right? Remember, just a positive integer is just really straightforward, like x to the 10th, x to the 7th, x to the 6th, whatever. The domains and ranges match either the x squared or the x to the 3rd, right? Either parabola or that cubic function. When you put it as a fraction, remember that's a root, right? That's a root. So it would be like x to the 1/2, x to the 1/3, and so on. I always feel bad when I do that. It's like I'm not saying anything about those people out there. It's just I want to quiet. And remember that the -1. I think we talked about this right at the end of yesterday. The -1, that's a reciprocal function or an inverse variation, something like that. So it'd be like 1 over x. That's a hyperbola. Remember, just a very general sketch of the graph. The parent would look like that with a vertical asymptote and a horizontal asymptote, which kind of leads just right into rational functions. So that's the next one that we'll talk about here. Rational functions is just basically a ratio of two polynomials. Okay, we did a whole chapter on rational functions in Honor Number 2. Okay, where you have p of x over q of x, where p of x and q of x are polynomials. Okay, they're polynomial functions. The domain of any rational function is just basically all values that just except the ones that make the denominator 0, right? As long as they have, well, I guess if they're polynomials, they wouldn't have any restrictions. So basically, q of x cannot be 0 because we can't divide by 0. Okay, so here's an example: 2x to the 4th minus x squared plus 1 over x squared minus 4. There's the graph down below. Okay. We could have talked through this one back in Honor Number 2. We've had graphs that kind of look like this before. But if I'm asking you for the domain, you look at what makes the domain equal to 0, and that's what x cannot be. So I would say x cannot be, x squared minus 4 cannot be 0. And then just solve that equation. Add the 4 over, square root it, you get x is not equal to plus or minus 2. That also means that there are vertical asymptotes at plus or minus 2. Remember the rules about horizontal asymptotes? Remember either if it's top heavy or bottom heavy, or if they're equal in terms of the degree. I believe if it's top heavy, it does it have one? I forget the rules. Oh, sorry. But I'm sure we'll talk a little bit more about that later on. But what we're looking at here is more just what's the domain and range, right? Remember, the domain is just all values such that the denominator, the polynomial denominator, cannot be 0. Okay. Now, this second to last one here, algebraic ones. Algebraic functions, it's kind of hard because it's just basically any sort of combination that you can have, adding, subtracting, multiplying, and dividing these other types of functions. Okay, it's just constructed using those different operations. Starting with, think about it this way. Starting with polynomials, at least. Any rational function is automatically an algebraic function because it has a division in it, right? It's a division of two polynomials. It's just a unique type of algebraic function. Ones that's only division by two polynomials. But these are other types of algebraic functions. And when you start working with algebraic functions, that's when you get really funky graphs. It had this figure 17 that it used down in the book. Those are just different graphs of algebraic functions, right? That's when you start having ones that, almost look parabolic and then maybe one side is skewed, or maybe, you have different parts of the graph. I don't have anything down below because obviously then that would be that would mean I would have negatives underneath the radical, right? So there's different things that can or can't happen in terms of each function. And each one is specific into itself, so that you kind of have to take each one as its own separate entity. There's no rules to follow for a lot of these algebraic ones, okay? But again, that's if you add, subtract, multiply, or divide any two separate types of functions, you can call it what's called an algebraic function. And then the last one we'll talk about is trigonometric functions. Trigonometric functions. This includes sine, cosine, tangent, secant, cosecant, cotangent, right? Trigonometric functions. I wanted to reference this here. Reference page 2. In the back of your book, there are reference pages that have all of like the trig identities and stuff in it. So just know that if you're like, oh man, what is that trig rule? What is that identity? They're all in the back of your book, and you can take a look at them there if you'd really like to. And calc, the convention is that we are always going to use radian measure. Okay, we're always going to be using radian measure. We're not really ever talking about degrees. Mostly, just about always, we're going to be using radian measure. Obviously, except one other one noted. For example, when we use the function f of x is equal to sine x, it is understood that sine x means the sine of the angle whose radian measure is x. Thus, the graphs are below here. Here's sine of x, here's cosine of x. Remember that sine of x starts at 0, 0, and then cycles through. Okay? Remember that we have a cycle here, and then if it kept going, and then if this kept going, there would be a cycle there, right? Cycles of the same values over and over and over again. Same thing for cosine, except for cosine starting here and here, 0 to 2 pi. We have wavelength, we have amplitude, we have phase shifts. We can, we'll talk about that a little bit more in the next section. Section 1.3, we talk about the different transformations that we can do with sine, cosine, and tangent functions. But the domain is always going to be all real numbers. Okay? I can plug in for x anything that I want for any of these trig values, but the range is restricted. The range, the output values only go from -1 to +1. Okay? Think about the unit circle, right? It never goes above or below -1 for the sine value. It never goes to the left or to the right of -1 or +1 for the cosine value. Okay? Remember, cosine is x, sine is y for the coordinates on the unit circle. Okay, so sine is always between -1 and +1. The sine of x is always between -1 and +1. Right? We know that based on the unit circle. Think about the coordinates along there. -1 to +1 for the x values, -1 to +1 for the y values. Okay. So I'm talking about the range values for those functions. Okay. In terms of absolute values, obviously, if we took the absolute value, they would just have to be less than or equal to 1. Also, remember that since these are cyclic, we can have different values that come up again, and come up again, and come up again, and come up again. If I asked you for where does, if you're thinking about the unit circle, that's an oblong circle there. If you're looking at the unit circle and I say, okay, where does the x value equal radical 3 over 2? Right? So what angle is cosine is radical 3 over 2? So this would be pi over 6, right? Is there another place where pi over 6 happens? Or excuse me, radical 3 over 2 happens? Yeah, it's right down here, right? Those two values have that same x value at, 11 pi over 6, right? Yeah, I had to remind myself of the unit circle there. 11 pi over 6, okay? And isn't this happening again there? And then again there? And then again there? And so on and forever, right? And same thing down here. So that when we have those values, we have to consider both all of the rotations plus 2 pi. Okay? And we'll talk about that a little bit more today here when we get to the next example. Okay. In terms, it's interesting to point out where they fall on the graph too. Like taking a look here, like if I've got pi over 6, pi over 6 would be somewhere right here, right? So if I'm thinking about the x value there, it would fall at all of those different moments, right? So you've got to think about where is it, not only where is it happening on the unit circle, but where is it also happening on the graph as well. Okay, so let's get to this example. Where is the domain of the function f of x is equal to 1 over 1 minus 2 cosine x? Okay. Now, you got to think about this. Are there any restrictions with cosine x? Are there any restrictions on, the domain of cosine x? No. Domain is negative infinity to positive infinity for cosine x. So there's no special restrictions that I have to plug for plugging into cosine x. Where does the restriction come? The denominator. This is my restriction, right? 1 minus 2 cosine x can never come out to be 0. If it comes out to be 0, then this is undefined, okay? So if I want the domain, I just have to solve this little equation that I've come up with here. Subtract the 1 over to the other side. I got negative 2 cosine x is equal to negative 1. Divide by the negative 2. Cosine x is equal to 1/2. Oh, not equal to. Okay, so where does cosine equal 1/2? Where does cosine equal 1/2? Don't use your calculator. Think about the unit circle. Where does cosine equal 1/2? Aaron, right? Not pi over 4. That would be the pi over 4 family is the radical 2 over 2. That's what you're thinking. The coordinates of the radical 2 over 2. Think about x value here. This is the radical 3 over 2, right? The pi over 6 family is the radical 3 over 2. So what is it? Pi over 3. Right? Pi over 3. Okay? So we can say that x is not equal to pi over 3. Where else does that happen then? Okay, well, if we're in this whole, yeah. It happens here, right? What other place on the unit circle has that same x coordinate? Right down there. And why are we focusing on the x coordinate? Because it's cosine. Okay, because it's cosine. If this had sine, we'd be looking for the y coordinates, right? Okay, so where does this have the same x coordinate here? Down there. So where is that angle? What is that again? 5 pi over 3. Okay. Now, anywhere else? Where else does that happen? Plus all rotations, right? So I know this is going to look weird, but this is what the formal domain would be. Set of all numbers x such that x is not pi over 3 plus 2 pi n, including all rotations, right? Or x is not 5 pi over 3 plus 2 pi n. Now, we brought up n, we brought up a new variable, and now we have to define what variable. What does n have to be? An integer. Any integer, such that n is an element of z. I should have put that on the same line, but I was worried that I was going to go off the edge of the screen over there. Okay, why an integer? Well, because that accounts for all negative rotations as well. Okay, if I plugged in -5, which is an integer, that would just be -5 rotations, right? 5 rotations in the negative direction. Okay, so that would be my domain here. Looks a little funky. Integer. Such that x is an element of an integer. All right. Okay. The tangent function is related to the sine and cosine functions. We all know tangent of x is equal to sine over cosine, right? Its graph is shown down below. Okay. So where is tangent undefined? Wherever cosine is 0, right? Tangent is undefined wherever cosine x is equal to 0. Where is cosine x equal to 0? Pi over 2 and 3 pi over 2, right? So that's why you see the vertical asymptotes there happening at pi over 2 and 3 pi over 2. Okay? So the domain is all set of all numbers x such that x is not pi over 2 or 3 pi over 2 plus the additional 2 pi rotations. Okay. All right, so let's talk about exponential. The exponential functions are the functions of the form f of x is equal to b to the x. Now the exponent is up in, the variable is up in the exponent, b to the x. So like 2 to the x, 3 to the x, 4 to the x, 5 to the x. 0.5 to the x is still exponential, but it's exponential decay rather than exponential growth. Any b value that is less than 1, greater than 0, is going to decrease rather than increase. Okay? Exponential functions will be studied in section 1.4. We will see that they are useful for modeling many natural phenomena. That's like, exponential growth, exponential decay, half-life, things like that. All of those get modeled by exponential functions. Okay? The domain, the set of all numbers such that x is all real, right? Negative infinity to positive infinity. The range has to just be greater than 0. Greater than 0. Not greater than or equal to 0. Greater than 0. Okay. And why not 0? Because if you plugged in 0, 2 to the 0 power would always just be 1. It would be a flat line of 1. All right. And now let's talk about logarithmic. Logarithmic. Remember, logarithmic is the inverse of exponential. So the domains and ranges flip. The domain of exponential was all real numbers. So now the range of logarithmic is all real numbers. The range of exponential was greater than 0, so therefore the domain is greater than 0. Okay? So logarithmic functions are f of x is equal to log base b of x, where the base is a positive constant. Got to be positive. They are the inverse of exponentials. We'll be studying those in section 1.5. This shows the graph of different logarithmic functions. Look, I'm just changing the base there. Okay? This is common log x, log base 10 of x. This is just decreasing the base as we go. Decreasing the base will bring the line up. Okay, we'll shift it this way. Okay, going from log base 10 to log base 2. You see that there. Again, the domain is starting at 0, going on up. The range is negative infinity to positive infinity. Okay. And again, we'll go into greater depth with these a little bit later. Okay, but this is just kind of like scratching the surface. This is like, oh, remember all those things you learned in Algebra 2? Yeah. Classify as one of the types. How would I classify the first one there? How would I classify that first function? 5 to the x. What would you classify that as? Okay. Yeah, go ahead. Exponential, right? Exponential. Exponential. Wouldn't say power there. Exponential. You wouldn't say power. Why not power? Because power is x to the number. Okay. Exponential is number to the x. Oh, and I kind of just said b. What's b? Power. You could also consider this polynomial too. Yes, a monomial is still a polynomial. So you could consider it polynomial, but a power is a unique type of polynomial because it's only just one term, x to that power. Okay. What would you consider c? Yes, I would consider that algebraic. Algebraic. I would consider that algebraic. You may consider it rational. I would not say rational because 1 plus x, 1 minus radical x is not a polynomial. And rationals are defined to be polynomials in numerator and denominator. Okay. And what about the last one there, d, u of t? 1 minus t plus 5t to the fourth. What do you think that one would be? Polynomial. Polynomial. What's the degree on that? 4. We would call that a quartic, right? Quartic, which is degree of 4. Cool. All right, that's section 1, 2, folks. Let me stop the recording.